This lecture covers conjugation. Conjugation occurs when there are overlapping p orbitals on 3 or more adjacent atoms. Now let's look at 1,3-butadiene and determine whether it's conjugated or not. So the first thing I'm going to do is draw the p orbitals that make up these pi bonds. So I've got these two p orbitals that overlap to form that pi bond, and I've got another two that overlap to form the second pi bond. So one criteria is satisfied. We've got p orbitals on 3 or more adjacent atoms. So all these are on adjacent atoms, and there are 4 atoms total. And if we think about the electron flow, we know that there's a bond here, so there's overlap here, and that there is a bond here. Since this is a planar molecule, it's completely sp2 hybridized, the electrons are not restricted to just these bonds. They can actually flow all over. And you can see that in this depiction, where this is the molecular orbital that is formed. There is a pi cloud that travels over all 4 of these carbon atoms above and below the plane. This is an example of a conjugated system where you have overlapping p orbitals on 3 or more adjacent atoms. Now let's look at 1,4-pentadiene. If I were to draw the p orbitals in 1,4-pentadiene, I've got these two p orbitals that make up this pi bond, and I've got two p orbitals here that make up the second pi bond. However, in the middle, I've got an sp3 hybridized carbon atom which has no p orbitals. And if you look at the 3D depictions, you can see that there's a pi bond here that's planar sp2 hybridized, pi bond here, planar sp2 hybridized carbons, and then you've got this sp3 hybridized carbon which doesn't have a p orbital. And so you can see that it's not overlapping over 3 or more adjacent atoms. You've got this one carbon that blocks the overlapping. And so this is not a conjugated system. This is an example of isolated alkenes, whereas this is an example of a conjugated diene. A final note about conjugation: just like when we talked about resonance, remember that delocalization of electrons increases the stability of the molecule. Now let's look at some properties of conjugated molecules. We'll look at the geometry, the possible conformations, the bond lengths of the carbon-carbon single bonds, and the stability of these molecules. Conjugated systems need overlapping p orbitals, and in order for overlap to occur, the p orbitals must be aligned and planar. This doesn't mean the whole molecule has to be planar, just the part with the overlapping p orbitals. If we look at this example, the cyclohexane we know is going to exist as a chair conformation, so it's not planar, but we're not interested in that part of the molecule because it has no p orbitals. We're interested in this carbon-oxygen nitrogen part of the molecule. We already can tell that this carbon-oxygen double bond implies that this carbon is sp2, this oxygen is sp2. That means they both have p orbitals, and that's what's forming the carbon-oxygen bond. If we have one more p orbital that is aligned, then we have a conjugated system. From this resonance form, we would think that the nitrogen is sp3. Now let's draw the other resonance form. So if I were to draw the arrows, I can show these electrons going down here and pushing these pi electrons up to the oxygen, which gives me no change in the cyclohexane, but now oxygen bears the negative charge, and there's a double bond to nitrogen. And from this resonance form, we can see that nitrogen is also sp2 hybridized. If the nitrogen is sp2 hybridized, then we have a p orbital on all these 3 atoms. We've got a p orbital on the oxygen, carbon, and nitrogen. They're adjacent, they're aligned and planar and overlapping. And so this is a conjugated system. Our nitrogen chooses to be sp2 instead of sp3 hybridized because delocalization stabilizes the system. So you have delocalization of electrons in a conjugated system, and that increases stability. Now let's talk about conformations. Now recall that stereoisomers have fixed geometry or configuration. So for instance, if we think about the R and S enantiomer or an E and Z alkene, in order to go from R to S or E to Z, we would actually have to break a bond to do that conversion. Conformers, however, are the same molecule. So we're not breaking any bonds here if we have to convert, we are just rotating about carbon-carbon single bonds. And these are also called conformational isomers. Let's look at the conformational isomers of conjugated dienes. This is again 1,3-butadiene. We can draw it in this way, where about the sigma bond we have the two alkenes on opposite sides. In this case, we call it S-trans. Trans for the fact that the alkenes are on opposite sides, and the S stands for the fact that we're talking about the sigma bond geometry. This is an equilibrium with its S-cis form. Remember that these are conformational isomers, so they keep rotating about this single bond and can convert from one to the other and back again. In the S-cis conformation, we've got both alkenes on the same side of the sigma bond, and this is the less stable form of this diene, and that's due to sterics. Now let's look at the bond length of carbon-carbon sigma bonds. So if we look at an sp3 hybridized carbon bonded to another sp3 hybridized carbon, the average bond length of this carbon-carbon bond is 153 picometers. Likewise, for an alkene, an sp2 hybridized carbon bonded to an sp2 hybridized carbon has an average bond length of 134 picometers. Now let's look at this conjugated diene. We've got 4 sp2 hybridized carbons. As we would expect, the double bond is 134 picometers. However, this single bond is 148 picometers, which is significantly shorter than the average single bond length, but not quite as short as a double bond. There are two possible arguments for this. One is a hybridization argument. In that case, we're saying that both these carbons are sp2 hybridized, and since we have greater S character in carbon sp2 bonds than in carbon sp3 bonds, we end up with a shorter bond. We have a second argument, and that argument is the resonance argument. So if you think of this diene, we can draw two resonance forms. One is this one, and then we can push the electrons in the opposite direction, and our second resonance form is this one. Overall, our resonance hybrid is telling us that we've got delocalization across all of these 4 carbon atoms, and so it's telling us that this bond actually has partial double bond character. And that explains why it's shorter. Both the hybridization and the resonance argument help explain this observed phenomena. Now let's look at the stability of conjugated molecules. We've already said that delocalization increases stability, which means that conjugated systems are more stable than the equivalent non-conjugated systems. The supporting evidence comes from the heats of hydrogenation. So if we were to take these 3 alkenes, we've got a conjugated diene and 2 non-conjugated dienes, so 2 isolated alkenes, and we can hydrogenate them until they form the corresponding alkane. In this case, we can see that the conjugated system is the most stable. This stabilization is called the resonance stabilization or the resonance energy. Now pause the video and circle the conjugated systems in each molecule before moving forward. In some cases, the conjugated system may be the whole molecule. In other cases, it may not. In each of these cases, if you have difficulty figuring out conjugation, try drawing resonance forms. Let's start with the first one. In this case, we know that these carbon atoms are sp2 hybridized and have p orbitals. We also know that a carbocation is sp2 hybridized, it's planar, and it has an empty p orbital. And so you can tell that this entire system is conjugated. We've got overlapping p orbitals on 3 or more adjacent atoms. And likewise for the allyl anion. In this case, let's also draw the resonance form. If we draw the resonance form, we can tell that all 3 carbon atoms in this allyl system are sp2 hybridized, and this whole system is also conjugated. Likewise for this radical. Remember that you can delocalize this radical using resonance and have a radical here as well as here in 2 different resonance forms. And I would recommend that you draw that for practice. And this whole system is also conjugated. Now let's look at the next 3 compounds. So for this compound on the left, we can tell that this part is going to be in conjugation. We've got a p orbital here, one here, one here, 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 and here. Now try and draw a resonance form and you will see that this oxygen can also participate in resonance with the system, and so this oxygen can choose to be sp2 hybridized in order to be in conjugation and become more stable. There are several different resonance forms, but we'll just draw one to show that we can do a conjugation. So this is one possible resonance form, and what it's showing is that this oxygen can be sp2 hybridized and therefore also has a p orbital. And so this entire system is also conjugated. If we look at this aldehyde, we can tell immediately that this aromatic group is conjugated. It's got 2 p orbitals here, 2 here, and 2 here. They're all adjacent, overlapping, and so this is all in conjugation. And we can also see that there are p orbitals in this carbonyl group here. So our entire conjugated system consists of this aldehyde as well as the aromatic group. In this case, we can see that there are p orbitals here and here for that pi bond, and another 2 here and here. So we can tell that this is our conjugated system. These 2 carbon atoms are not conjugated. They're sp3 hybridized carbon atoms, and they do not have p orbitals. And now let's look at beta carotene. Beta carotene is the orange pigment in carrots, and you can see that it's got a huge conjugated system. You can draw resonance forms for this system if you want. It will take a while, but this is the conjugated system where everything is sp2 hybridized, has p orbitals, they're all adjacent to each other. The rest of this molecule has sp3 hybridized carbon, and it is not in conjugation.